The Pantheon in Rome has stood for nearly 2,000 years with a concrete dome so massive that it remains the world's largest unreinforced concrete dome even today, outlasting every modern concrete structure built in the past century. Meanwhile, modern highways and bridges made with a supposedly superior concrete begin cracking and crumbling within decades, requiring constant repair and eventual replacement. Roman concrete structures have survived millennia of earthquakes, temperature changes, and seawater exposure while getting stronger over time. Yet the formula that created this wonder material was completely lost for over 1,000 years. We're only now beginning to understand how the Romans made concrete that was not only stronger than ours, but could actually heal its own cracks, grow more durable with age, and laugh at the forces that destroy modern construction. This isn't just an ancient building material. This is a 2,000-year-old technology that we're frantically trying to recreate because it's better than what we have today. Concrete is so ubiquitous in modern construction that we barely think about it. It's the second most used substance on Earth after water, with over 10 billion tons produced annually. We assume our concrete is the pinnacle of material science, the result of centuries of refinement and modern chemistry. But walk through Rome, and you'll find structures built 2 millennia ago that put our concrete to shame. The Pantheon, completed around 125 CE, features a dome spanning 143 feet that has stood without reinforcement for 1,900 years. No modern concrete structure has lasted even a fraction of that time without significant maintenance or reinforcement. The secret wasn't just in what the Romans used, but how they combined materials in ways we didn't understand until very recently. Roman concrete, or opus cementitium as they called it, was fundamentally different from modern Portland cement concrete. The Romans made their concrete using volcanic ash, lime, seawater, and volcanic rock aggregate. This combination created a material with properties that modern engineers are only now beginning to appreciate and attempt to replicate. The Romans didn't invent concrete, but they perfected it and used it on an unprecedented scale. Earlier civilizations had primitive cement-like materials, but the Romans developed concrete into a versatile construction material that could be molded into any shape, set underwater, and endure for millennia. They used it everywhere, in buildings, aqueducts, harbors, roads, and monuments. The scale of Roman concrete usage was staggering, rivaling modern consumption when adjusted for population. The key ingredient was volcanic ash, specifically a type called pozzolana, named after the town of Pozzuoli near Naples, where high-quality volcanic ash was quarried. This ash contains silica and alumina that react with calcium hydroxide from lime in the presence of water, creating what's called a pozzolanic reaction. This reaction produces calcium aluminum silicate hydrate crystals that bind the mixture together into an incredibly strong, durable material. The Romans discovered that mixing this volcanic ash with lime and seawater created something remarkable. When they used this concrete in marine environments, building harbors, piers, and breakwaters, something unexpected happened. Instead of eroding in seawater like modern concrete does, Roman concrete actually got stronger. The seawater triggered chemical reactions that caused the concrete to continuously develop more binding minerals over centuries, increasing its strength and durability the longer it was exposed to the ocean. This is the opposite of what happens with modern concrete. Our concrete is based on Portland cement, developed in the early 19th century. Portland cement concrete is strong initially, but degrades over time, especially in harsh environments. Seawater is particularly destructive to modern concrete because salt water penetrates the material, corrodes the steel reinforcement inside, and causes the concrete to crack and crumble. Most modern marine structures require extensive maintenance and have design lives of 50 to 100 years at most. Roman concrete marine structures, by contrast, have survived 2,000 years and are still standing strong. The ancient harbor at Caesarea in Israel, built by King Herod using Roman concrete around 15 BC, remains largely intact after 20 centuries of wave action and seawater exposure. Analysis of concrete samples from this and other Roman marine structures revealed something shocking. The concrete was stronger now than when it was built. Scientists studying Roman concrete discovered that seawater infiltrating the material triggered a rare mineral called aluminum tobermorite to crystallize within the concrete matrix. This mineral reinforces the concrete from within, filling microscopic cracks and voids, essentially causing the concrete to heal itself and grow denser over time. This process continues for centuries, meaning Roman concrete in seawater becomes increasingly durable rather than degrading. This self-healing property was completely unknown to the Romans. They didn't understand chemistry. They just knew empirically that their concrete worked remarkably well in marine environments. Through trial and error over generations, they refined their recipes and construction techniques, creating a material whose full properties they couldn't explain, but could certainly exploit. The volcanic rock aggregate the Romans used also contributed to material's durability. Instead of the crushed stone or gravel used in modern concrete, Romans often used chunks of volcanic tuff, pumice, or other volcanic rocks. These materials had rough, irregular surfaces that created exomechanical bonding with the cement paste. The volcanic nature of the aggregate also meant it could participate in the ongoing pozzolanic reactions, contributing to the concrete's long-term strengthening. Temperature played a role too. Modern Portland cement concrete requires high-temperature firing of limestone and clay at around 1,500 degrees Celsius, an energy-intensive process that also produces significant carbon dioxide emissions. Roman concrete used lime that was fired at much lower temperatures, around 900 degrees Celsius. This meant less fuel consumption and lower carbon emissions, making Roman concrete far more environmentally sustainable than modern concrete. The mixing process was also different. Romans mixed their concrete much less thoroughly than we do, creating a more heterogeneous material with varying compositions throughout. Modern concrete engineers would consider this poor quality control, but it turns out this heterogeneity actually benefits Roman concrete. The variable composition creates a more resilient material that can accommodate stresses in different ways across its structure rather than developing uniform weaknesses. After the fall of the Western Roman Empire in the 5th century CE, knowledge of concrete making was largely lost in Europe. The specialized skills, the understanding of which volcanic ash to use, the proper mixing ratios, and the construction techniques all faded as the social and economic structures that supported such specialized knowledge collapsed. For over 1,000 years, Europeans couldn't replicate Roman concrete, which is why medieval European architecture relied primarily on stone masonry rather than concrete construction. The rediscovery began in the 18th century when engineers started analyzing surviving Roman structures, trying to understand how they were built. The development of Portland cement in 1824 by Joseph Aston provided a new concrete technology, but it was based on different principles and materials than Roman concrete. Portland cement became the global standard, and for nearly 2 centuries, Roman concrete was considered an interesting historical curiosity, but not practically relevant. That changed in recent decades as modern concrete's limitations became increasingly apparent. Infrastructure decay, the enormous carbon footprint of cement production, responsible for about 8% of global CO2 emissions, and the short lifespan of concrete structures in harsh environments prompted researchers to take a fresh look at Roman concrete. If the Romans could make concrete that lasted 2,000 years and got stronger in seawater, perhaps we should figure out how they did it. Modern scientific analysis has been revelatory. Using electron microscopy, X-ray diffraction, and other advanced techniques, researchers have examined Roman concrete at the molecular level. They've identified the specific minerals present, traced the chemical reactions that occur over time, and determined which components contribute to which properties. What emerges is a picture of a remarkably sophisticated material that the Romans developed through empirical observation, but that we can now understand through modern chemistry. One crucial discovery involves lime clasts, small chunks of lime that appear throughout Roman concrete. For years, scientists thought these were impurities, evidence of incomplete mixing or poor quality control. But recent research suggests they serve an important function. When cracks form in the concrete, water infiltrates and reacts with these lime clasts, dissolving them and causing them to precipitate as calcium carbonate that fills the cracks. This is the self-healing mechanism in action, and it works for centuries. The implications for modern construction are enormous. If we could create concrete with Roman properties, durability measured in millennia rather than decades, self-healing capabilities, increasing strength over time, we could revolutionize infrastructure. Buildings, bridges, dams, and marine structures could last far longer with minimal maintenance. The environmental benefits would be substantial too. Less frequent replacement means less concrete production, reducing carbon emissions and resource consumption. Several research teams worldwide are working on recreating Roman concrete or developing modern variants incorporating Roman principles. The challenges are significant. Volcanic ash of the right type isn't available everywhere, and the specific pozzolanas used by Romans came from particular volcanic regions around the Mediterranean. Seawater contains impurities and variable composition that complicate industrial use. The slower setting time of Roman concrete, it takes decades to fully develop its strength, isn't compatible with modern construction schedules where buildings need to be usable quickly. However, progress is being made. Researchers have identified modern volcanic ashes and industrial byproducts like coal fly ash that can serve as pozzolanic materials. They're developing concrete recipes that incorporate Roman principles while working within modern construction constraints. Some experimental structures have been built using Roman-inspired concrete, and long-term monitoring is underway to see if these modern interpretations can achieve even a fraction of the durability of authentic Roman concrete. The economic incentive is strong. The American Society of Civil Engineers estimates the United States alone needs to spend over $2 trillion on infrastructure repairs over the next decade, much of it replacing degraded concrete structures. If more durable concrete could extend infrastructure lifespan even modestly, say from 50 years to 100 years, the savings would be enormous. If we could approach Roman concrete's durability, we could transform infrastructure economics entirely. There's irony in the fact that we're trying to recreate a technology perfected 2,000 years ago by a civilization that didn't have modern chemistry, electron microscopes, or computer modeling. The Romans couldn't explain why their concrete worked, but through generations of experience, they developed recipes and techniques that produce superior results. They optimized through empirical observation, what we're now trying to understand, and replicate through scientific analysis. This isn't the only example of lost ancient technologies that surpass modern equivalents. Damascus steel, Greek fire, Stradivarius violins, and various pigments and dyes represent cases where ancient practitioners achieved results we struggle to match despite our advanced understanding. In some cases, this reflects lost tacit knowledge, skills that were taught through apprenticeship and demonstration rather than written down. In others, it reflects different priorities. Ancient craftsmen optimizing for longevity and quality rather than speed and cost. Roman concrete definitely involved tacit knowledge. Written sources from antiquity provide some information about concrete making, particularly Vitruvius's architectural treatise De Architectura from the 1st century BC. But these texts don't capture all the practical details a master builder would know. Which specific ash to use, how thoroughly to mix, how long to cure, how to judge proper consistency. These skills were learned through years of practice under experienced masters, and when that chain of knowledge transmission broke, the expertise vanished. Modern attempts to recreate Roman concrete face another challenge. We can analyze surviving structures, but these represent only the successful applications. We don't see the Roman concrete that failed, the experimental batches that didn't work, or the structures that collapsed within decades. Survivorship bias means we're studying the best examples of Roman concrete, the structures that happen to be built with optimal recipes in suitable conditions. Achieving consistent results across variable conditions would have been challenging even for Roman builders, and it remains challenging today. Nevertheless, the potential benefits justify continued research. Climate change makes infrastructure durability more critical as extreme weather events increase. Resource constraints make material efficiency more important, and the sheer volume of concrete we use, over 30 billion tons globally during the typical lifespan of a modern concrete structure, means even small improvements in durability would have massive environmental and economic impacts. Some researchers are taking the Roman example even further, looking at biological inspiration. If concrete could be designed to actively heal cracks using bacteria that precipitate calcite when cracks form and water infiltrates, we could create truly living building materials that maintain themselves. This bioconcrete approach is inspired partly by Roman self-healing concrete and partly by natural processes like coral growth and shellfish shell formation. The Pantheon remains the most spectacular demonstration of what Roman concrete could achieve. Standing beneath its dome, looking up at the oculus open to the sky, you're experiencing a space that has remained essentially unchanged for 1900 years. The concrete dome has never been reinforced, never been significantly repaired, yet it stands strong, still the largest unreinforced concrete dome ever built. Every modern concrete dome requires steel reinforcement. The Pantheon needed none. Engineers analyzing the Pantheon discovered the Romans used different concrete recipes at different heights in the dome. Heavier aggregate at the base provides strength where loads are greatest, while lighter pumice aggregate at the top reduces weight, where structural demands are less. The thickness varies too, tapering from about 20 feet thick at the base to less than 5 feet at the oculus. This optimization shows sophisticated understanding of structural engineering principles, achieved without modern mathematics or computer modeling. Walking through Rome, you encounter Roman concrete everywhere. The Colosseum's foundations, aqueduct channels, the massive walls of baths of Caracalla, the base of Trajan's column, all concrete, all still standing after 2 millennia. Then you notice modern concrete structures built mere decades ago already showing cracks, spalling, and degradation. The contrast is humbling and instructive. Roman concrete teaches us that newer isn't automatically better, that technological progress isn't always linear, and that ancient civilizations achieve remarkable feats we shouldn't dismiss as primitive. The Romans solved problems we're still struggling with, using materials they found in their environment and techniques they refined through experience. Understanding how they succeeded offers both practical benefits for modern construction and a healthy dose of humility about our assumptions of technological superiority. The lost formula of Roman concrete wasn't really lost because of lack of documentation, though better written records would have helped. It was lost because the social structures that supported specialized knowledge transmission collapsed. Master builders who would teach apprentices disappeared. The trade networks that supplied specific volcanic ash broke down. The economic system that funded large-scale construction projects evaporated. Knowledge embedded in practice vanishes when practice stops, regardless of what's written down. Today, as we reverse engineer Roman concrete and try to incorporate its principles into modern materials, we're not just recovering a lost formula, we're reconnecting with ancient knowledge, bridging a gap of nearly 2,000 years, and perhaps learning to think differently about materials, durability, and what we want from our built environment. Roman concrete reminds us that solutions to modern problems might lie in understanding what ancient people got right, combining that wisdom with modern scientific understanding, and creating something new that honors both past and present.